Welcome to the 10th video on compressible fluid flow. My name is Redishtia, Assistant Professor from the Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. In this video, we will go through the critical state relations and choking in isentropic fluid flow. Let us start with the critical state relation for isentropic flow. We know that the static temperature and stagnation temperature are related by the equation shown in the first slide. That is T0 divided by T is equal to 1 plus gamma minus 1 by 2 m square. If the static state corresponds to the critical state, then Mach number m becomes equal to 1 and T can be represented as T star. If we substitute m equal to 1 and replace T by T star in the first equation, we arrive at our second equation, that is T0 divided by T star is equal to gamma plus 1 divided by 2. The first equation connects the static temperature at any point on the flow field with its corresponding stagnation temperature, whereas the second equation connects the temperature at the critical state in the flow field to the stagnation temperature at the critical state of the flow field. Since it is an isentropic flow, the stagnation temperatures remain constant, because in an isentropic flow, stagnation enthalpy is a constant. Enthalpy can be written as Cp into T. For stagnation enthalpy, we can write it as Cp multiplied by T0 is equal to a constant. For a perfect gas, Cp remains constant, hence we can write T0 is equal to a constant. So taking this to our advantage, we can obtain the relation between the temperature at critical state and the temperature at any particular point in the flow field by dividing the first equation with the second equation, and we obtain at the equation number 3 that relates the critical state temperature with the static temperature of fluid at any point on the flow field. Since this is isentropic flow, the PVT relationship for isentropic flow holds good here also. So we can write P star by P is equal to T star by T raised to gamma by gamma minus 1. Substituting for T star by T, we arrive at the fourth equation that connects the pressure at critical state with the static pressure of fluid at any point on the flow field. Similarly, we arrive at the relation connecting the density at static state with the density at any point on the flow field. Apart from all this, there is another important quantity that has to be non-dimensionalized for use in isentropic flow. That is the variation in the flow area, or also known as the cross-section area of flow. The variation in all these properties are due to the variation in cross-section area. Hence, we have to express area in a non-dimensional manner. Hence, we express the cross-section area or the flow area in non-dimensional form using the cross-section area at the critical condition. This term is written as A by A star and is known as area ratio. The term area ratio is of great importance in the study of isentropic flow and for the analysis of nozzle and diffuser. In order to obtain the relation of A by A star, we use the continuity equation as applied to isentropic flow. We can write by applying the continuity equation at a static condition and at a sonic condition as rho AC is equal to rho star A star C star. We rearrange it to write A by A star, that is area ratio, as rho star by rho multiplied by C star by C. Note that C star by C can be written as A star by C because C star is the velocity of fluid at critical condition where Mach number is 1, which means the fluid velocity and sound velocity are equal at that particular point. So C star is equal to A star, which can be written as 1 by M star. We have the relation rho star by rho in terms of gamma and Mach number, and in previous video while studying about reference velocity we expressed M star in terms of gamma and Mach number. Substituting these relations we will get a relation for A by A star in terms of gamma and Mach number, which is shown by the final equation. Using this equation, we can plot the change in A by A star with respect to Mach number. The plot obtained is shown in the figure. When A by A star is equal to 1, that means the static condition corresponds to the sonic condition. At that point, Mach number is equal to 1, which is represented by the dashed lines joining x-axis and y-axis. For all other values of A by A star, we see that there are two values of Mach number. That is, if you take a particular value for A by A star and plot it to this curve, we will get a Mach number corresponding to this value, and also we get a Mach number corresponding to this value. And we see that the first value lies in the subsonic region, whereas the second value lies in the supersonic region, which is separated by this dashed line that represents sonic condition. Hence, for all value of area ratio other than 1, there is two values of Mach number. One lies in subsonic region and the other lies in supersonic region. Now let us see how we can express mass flux in terms of Mach number. From the continuity equation, we know that mass flow rate is equal to rho AC. When we divide it by the cross-section area A, we get the mass flux, which is equal to rho multiplied by C. If we substitute the relations connecting the static condition with the stagnation condition, we will be able to obtain the mass flux in terms of Mach number as given by the equation shown here. In this, what we have is gamma, capital R, which are fixed for a particular gas. P0 represents the maximum pressure, that is stagnation pressure. T0 represents the maximum temperature, that is the stagnation temperature, which are constant for an isentropic fluid. And the only variable term in this equation is Mach number. If we differentiate this equation with respect to Mach number and equate it to 0, we will get the condition for maximum mass flux, which is obtained to be plus or minus 1. Taking the positive value for Mach number, we see that the mass flux is maximum when Mach number is equal to 1. If we substitute m equal to 1 in this equation, then the equation reduces to the following form. Note that when m has been substituted 1, the cross-section area A is replaced by A star. That is, m becomes equal to 1 at sonic condition, so the area corresponding to sonic condition is represented as A star. So this equation corresponds to the maximum mass flux equation. Here, the mass flux becomes maximum if the cross-section area is minimum. So we can also infer that when Mach number becomes maximum, that is when the mass flux becomes maximum, the Mach number becomes equal to 1, and that is obtained at the point of least cross-section area. In a duct, the region of least cross-section area is referred to as throat of the duct. Therefore, we can say that if the mass flux is maximum, then Mach number is equal to 1 at the throat of the duct. When the mass flux is maximum, we say that the flow through the duct has been choked. That is, it is flowing to its fullest, and further increase in mass flux is not possible. The condition is referred to as choking, and the condition of choking is attained in an isentropic manner. Hence, it is sometimes referred to as isentropic choking.